Welcome to Lecture 3. Lecture 3, third law of thermodynamics. This one is about how we calculate entropy or measure entropy. So we have to introduce a new concept called heat capacity of a closed system. Remember, closed system means there's no exchange of mass between the system and its surroundings. So we do the heat measurement under constant pressure. We'll put a heat flow into the system, and we measure temperature change. So the ratio of these two is heat divided by dT, give us the heat capacity. So the definition of heat capacity. The example of heat capacity shown for a compound cerium nickel for silicon here is showing heat capacity is the joule per mole per Kelvin as a function of temperature, which is the absolute temperature Kelvin. As here it goes from 0 Kelvin and 0 heat capacity all the way up, increase when temperature goes up. So what is the entropy change then? We know the entropy change is dQ over T. So now dQ would be Cp divided by times dt. So the Cp divided by T times dt, that gives the entropy change. So we need to know Cp over T. So shown for the same compound here, the Cp over T as a function of temperature. As you can see, it's almost go to 0 at 0 Kelvin. But of course, we can never reach 0 Kelvin by experiments. But we can extrapolate to 0 Kelvin. So by making many measurements, people found that by experimental observations, when T close to 0 Kelvin, this heat capacity moves close to 0 Kelvin, and the Cp over T also moves to 0. So that means ds is equal to 0 at close to 0 Kelvin. So people developed the third law. Is that when temperature equals 0 Kelvin, for a system, its entropy also equals 0. So there are many discussions whether the system is stable or metastable or even unstable at 0 Kelvin, whether entropy equals 0 or not. But the fact is that for any measurement we do, and when temperature goes to 0, heat capacity and Cp over T goes to 0. That means entropy of any system at 0 Kelvin should equal to 0. So then if we measure heat capacity from 0 Kelvin or very close to 0 Kelvin to find out temperature, then we do integration. For Cp over T integration for 0 K to find a temperature, then we can calculate the entropy at each temperature at any given temperature by the integration. Okay. So what it means is that by experiment we measure heat capacity to very low temperature to high temperature, then we can calculate the entropy as a function of temperature. Okay, there's a couple more examples of a third law of thermodynamics here. So one is for ion, there's a BCC ion. The ion is BCC at low temperature. You see the heat capacity goes to 0 at 0 Kelvin, close to 0 Kelvin. And if you plot Cp over T, you can see that it also close to 0 Kelvin. Close to 0 at 0 Kelvin. For polymer, PTFE polymer, you can see that the heat capacity goes to 0 at 0 Kelvin, and the Cp over T also goes to 0 at 0 Kelvin, or close to 0 Kelvin. So we have shown for pure metal, pure element, and for compounds, for polymers. Entropy goes to 0 at 0 Kelvin. So that's the third law of thermodynamics. Of course, we know that we cannot measure 0 Kelvin, right? But so that cannot be proved by experiments. However, the trend we observed shows that. So third law means entropy of a system equals to 0 at 0 Kelvin. Oh, sorry, this is Cp over T. That's right. This is heat capacity at low. This heat capacity at low temperature scale. And this is Cp over T is here. Thank you. So next lecture is lecture 4. It's on the combined law of thermodynamics. Put the first law and the second law together. Thank you.